Hey everyone, and welcome. Today, we're going to dig into the origin story of what is, no joke, the single most powerful identity in all of trigonometry. So, where did this mathematical superstar even come from, and what makes it so incredibly important? Let's find out. So, what is this hero identity we're talking about? And really, why should you care? Well, it turns out that this one super elegant equation is the secret key to solving a massive range of problems. Everything from simplifying gnarly expressions in calculus all the way to, believe it or not, pinpointing your exact location on a map.
And you know, like any great superhero, this identity has an awesome origin story. It didn't just appear out of nowhere, it was actually born from smashing together two fundamental ideas that you probably already know really well. And here they are, the two parent concepts. Over on the left, you've got the good old Pythagorean theorem for right triangles. A squared plus b squared equals c squared. You've known that one for years. And on the right, the core definitions from the unit circle, that any point's x-coordinate is just the cosine of the angle, and its y-coordinate is the sine.
So what happens when we take these two absolute powerhouses of math and bring them together? Well, you get a proof that is so simple and so beautiful, it's basically a work of art. Let's watch how they fuse.
Okay, so it all kicks off with the basic equation for the unit circle. X squared plus y squared equals 1. And really, this is just the Pythagorean theorem in disguise, right? The radius of the circle is the hypotenuse, and its length is just 1. Now, since we know that x is cosine theta and y is sine theta, we just swap them in. We substitute. And this is the magic moment. You get cosine squared plus sine squared has to equal 1. It's that simple.
And boom, there it is, the big reveal. We usually write it as sine squared theta plus cosine squared theta equals 1. This is our hero, the Pythagorean identity. And the amazing part is, it's true for literally any angle you can possibly dream up. So, the big question is, what can we do with it? This identity's real superpower is its incredible ability to solve for the unknown. Think about it. If you know the sine of an angle, you can instantly find its cosine. And if you know the cosine, boom, you can find the sine. It's a ridiculously powerful tool.
You can see that right here. With just a little bit of algebraic shuffling, we can rearrange the identity to get sine squared all by itself or cosine squared all by itself. These other forms are just as important as the original, and trust me, they will save you a ton of time when you're trying to solve problems.
All right, let's put this thing to work with a pretty straightforward example. We're told that the sine of some angle is 3/5, and we know that angle lives in the first quadrant. Our mission, should we choose to accept it, is to find the cosine. Okay, first step, we plug in 3/5 right where sine theta is. Square that, and we get 9/25. Then we subtract that from 1, which tells us the cosine squared is 16/25. Now here comes the most crucial step. Do not miss this. When we take the square root, the answer could be positive 4/5 or it could be negative 4/5. So how do we know which one to pick? Well, that's what the quadrant information is for. We're in quadrant I, where the x value, which is cosine, is always positive. So our final answer has to be positive 4/5.
All right, you ready to level up? Let's try one that's a little trickier. This time we're given the cosine. It's negative 5/13, and the angle is down in quadrant 3. We need to find the sine. But don't worry, the game plan is exactly the same. Now, to save a little time, let's start with one of our rearranged forms. We'll plug in negative 5/13 for cosine. Now remember, when you square a negative number, it becomes positive, so that's 25/169. We subtract that from 1, and we're left with 144/169. And here we go again. That all-important square root step gives us two possible answers, plus or minus 12/13. So we check our location. We're in quadrant 3, where the y value, or sine, is negative. So our final answer must be negative 12/13. See? Same logic.
Now look, even superheroes have their kryptonite. And for students using this identity, there are two super common traps that people fall into all the time. Let's make sure you know what they are so you can avoid them. Okay, the number one biggest mistake, hands down, is forgetting about the plus or minus sign when you take a square root. Math gives you two potential answers. It's your job, using what you know about the quadrants, to figure out which one is the single correct answer. If you skip this step, you're literally just flipping a coin, and you're going to be wrong half the time. The second trap is just forgetting the squares. It's so tempting. I get it. Sine theta plus cosine theta equals 1 looks so much simpler, right? But it's just plain wrong. It's not a real identity. The real power, the magic of this relationship, comes from those squares. They are absolutely essential.
Without them, the whole thing just falls apart.
So you might be sitting there thinking, okay, this is cool for my math test, but when am I ever actually going to use this? Well, this little identity isn't just trapped inside a textbook. It is fundamental to technology that you probably use every single day. Believe it or not, the GPS in your phone relies on this exact identity. See, calculating a position on a curved surface like Earth involves some pretty hairy math. This identity acts like a fundamental law of the universe, a mathematical check that makes sure all the calculations for latitude and longitude stay consistent and accurate. It's one of the core rules that keeps the whole global system from falling apart.
So we'll end with this thought. We have this one beautiful, simple rule that perfectly governs how points behave on a circle. It makes you wonder, right? What other elegant, fundamental rules are out there just waiting for us to find them, that govern all the other shapes and complex systems in our entire universe?